Okay, so we're going to be covering the topic of geometric series. Recall, just to review for a moment, that a series is a sum of infinitely many terms. So A1 plus A2 plus A3, so on and so forth. And it turned out that this was equal to the limit as k goes to infinity of the kth partial sum. So the sum n equals 1 to k of a sub n. That was the definition of the convergence of a series. And remember, we were basically saying, okay, to make sense of adding up infinitely many terms, we add up k of them. Then you can get an expression in k, and then send k to infinity. And that's effectively getting all of these terms added up. A geometric series is a series where each term after the first is a fixed multiple of its preceding term. In other words, for some real number, little r, which we'll call the ratio, to get the an plus 1 term, you take the an term, the previous term, and multiply it by r. And this is true for all terms after the first term. The way to really think of a geometric series is here. Typically, you have some constant hanging out in all the terms. We call that a. And a we'll often think of as the first term. And then you see that to get each term, you just multiply the preceding term by r. So here you have ar. If you multiply that by r, ar squared. Multiply that by r, ar cubed. So on and so forth. And with about a page of algebra, you can derive this expression for the kth partial sum. And so remember, the series itself, if it does converge, it will converge to the limit of the kth partial sum. So look at this, and you can get a sense for the rules for convergence of a geometric series. Think about what conditions you need on R for this to be something finite. K plus 1. So k is going to infinity and it's integer valued. So think of this k plus 1 as some enormous exponent, r to the 1 million plus 1. Well, in order for this whole term here to be finite, we're going to need this r to the k plus 1 term to go to 0. And the only way that happens is if r in absolute value is smaller than 1. If you have a number that's in absolute value smaller than 1 raised to increasingly larger and larger powers, the result will be the entire term will shrink to 0. If r is bigger than 1, say if r was 2, then you'd be getting 2 to some enormous power, where the power is getting bigger and bigger. So the thing would blow up. So that's really the key, is that we see here that as k goes to infinity, s sub k is approaching, and we should add this, there's one thing missing here. This is actually multiplied by a. So as k is going to infinity, this term is dropping to 0 if r is smaller than 1 in size. So as k is going to infinity, sk is approaching a over 1 minus r for absolute value of r less than 1. And that is the main result for geometric series. So for the geometric series as described above, the series converges if the absolute value of r is less than 1. In that case, it converges to a over 1 minus r. Otherwise, it diverges. And so geometric series are probably the most natural and handy series to work with. Because once you identify a series as geometric, all you need to do is determine what this R is, and that gives you your convergence criteria. So let's return to this standard example to get a feel for this. Here we have a geometric series, and we can see that to get from one term to the next, we multiply by 1/2. Usually a geometric series, you may have a constant. In this case, there is not one, but you could have something like maybe a 3 here, which you could factor out. But in this case, or in geometric series, you can typically see something written as something raised to the n power. So in this case, we see that the ratio is 1/2. And the absolute value of 1/2 is 1/2, which is less than 1, so it converges. And further, it converges to a over 1 minus r. And coming back here, a is always the first term. So in this case, a is 1/2. So this series converges to a over 1 minus r, or 1/2 over 1 minus 1/2, or 1/2 over 1/2, or 1. So when we add up all the terms in this series, we get exactly 1. To move on to another example, sometimes you may have a series that has some kind of geometric series embedded inside of it, but you need to fish it out. This is a perfect example of that. So we look here and we see something to the n power in the denominator, something similar to the n power in the numerator, but not quite. And so what we want to do is algebraically manipulate this summand to get something that is a fixed number raised to the n, which we will then know as a geometric series. So here, we can use our rules for exponents. So we know 3 to the 3n plus 1 can be written as 3 to the 3n times 3 to the 1. 2 to the n in the bottom we leave alone. And then we note that 3 to the 3n we can rewrite as 3 cubed to the n. And now we're just about there. So this 3 we can factor out. So this is the sum n equals 1 to infinity. Well, 3 times that sum. And we have 9 to the n over 2 to the n, or sum n equals 1 to infinity times 3 of 9 over 2 to the n. And now we identify this series as a geometric series. And its ratio term is the base. And we see that its r is 9 over 2. Well, that's bigger than 1. So that means that this series diverges. Intuitively, you can think of it as each term in the series is 9/2 times the previous term. So each term in the series is 4.5 times the previous term, which means the terms are getting bigger and bigger and bigger. The terms are blowing up. So when you add them all up, you get something infinite. But this is a very common type of problem where you have to manipulate things algebraically to then reduce things to an expression with a geometric series. But it always comes down to the same issue. Once you identify the geometric series, you identify the ratio, which gives you your convergence criteria. If it's bigger, if in absolute value it's bigger than or equal to 1, then it actually diverges and you're done. One more example. This is a fun thing to see when you get to this point in calculus, because your whole life in math so far, you've been told what it means to be a rational number. So remember, a rational number is a number that can be expressed as the ratio of two integers. And you're typically told that it's non-repeating decimals. So something that has a finite number of decimal points, digits after the decimal point, that's easy to see as a ratio of two integers. If it was 0.789, you know that that's 789 over 1,000. But what about the case where you have a repeating pattern in the decimal? How do we write that as the ratio of two integers? Now, we pick one here that we all know the answer. We all know that this is going to be equal to 2/3. But how do you actually derive that? And the answer is using geometric series. So we take this expression and we rewrite it by breaking it up in terms of these integers, well, these terms after the decimal one at a time. So first we have the first digit, which is 0.6. Then we have the second digit, which is 0.06. Then we have the third digit, which is 0.006. And hopefully you see where we're going with this. The fourth digit, which would be 0.0006, so on and so forth. And each one of these terms can be written as a fraction. This is 6 over 10 plus 6 over 100 plus 6 over 1,000 plus 6 over 10,000 and now note there's a 6 common to all of these terms, so we can factor that out. So this is 6 times a tenth plus a hundredth plus a thousandth plus a 10,000th, so on and so forth. But now note that each one of these terms is a power of 10. So the first term is 1 over 10. The second term is 1 over 10 squared. The third term is 1 over 10 cubed. Fourth term is 1 over 10 to the fourth. And we recognize that what we have in square brackets here is a geometric series. This is equal to 6 times the sum. Notice that you have to be kind of careful what you start your series at. The first term in the series is a tenth, so we would say that this is 1/10 to the n. So the first term has to be a tenth, so we want to start at n equals 1. So the first term is 1 over 10 to the 1. But again, this is a geometric series where r is 1 over 10. That means it will converge, so the absolute value of r is a tenth, which is less than 1. So we converge. And remember, it converges to a over 1 minus r. So this series converges to 6 times a over 1 minus r. Don't forget about that 6 that was out front. A, remember, is always the first term. 1/10. R, we identified also as 1/10. So 1 minus 1/10 in the denominator. And then we just work out what that is. So this is 6 times 1/10 over 9/10. Those tenths cancel. So we get 6 over 9 or 2 over 3. And this is how you show any repeating decimal question. Any repeating decimal can be written as the ratio of two integers, and this is how you do it. This is how you use geometric series to show that. Just to show a more complicated example, if you had something like, say, 0.53. So that would be repeated. So 0.535353. You would take a very similar approach, but you would break up pairs of digits in this case. So your first term would be 0.53. Your second term would be 0.0053, picking up that second 53. And then your third term would be the 000053. And then you would use the same, whoops, it should be a 53, not a 50. You would use the same type of analysis now to write each one of these terms as a fraction. And then you would factor out a 53 and see what the geometric series, the resulting geometric series would be. So geometric series are, I think most people would say, the most important type of series. We are going to refer back to geometric series a lot. And as we learn about different types of series and different ways to address convergence of series, geometric series will be something that we will go back to a lot. It's really the simplest type of series, so it's something that you want to have really mastered and down pat. We will refer to it quite a bit in the future.